Okay, welcome everybody. So the first speaker of the afternoon session is Isaeva from the University of Amsterdam. Isaeva is a world-leading expert in growing these magnetic topological materials based on binary decalcogenides. And today she's going to talk about the intermixing disorder in the intrinsic magnetic topological insulator based on manganese and, as I said, this binary decalcogenide studied by X-ray diffraction and bulk magnetometry. So Anna, please, the word is yours.
Thank you very much, Maya, for the nice introduction. Good afternoon, everyone. Thanks a lot for being here for my talk. I'm very excited that we can finally exchange science and be at this conference 1 year later. So as announced, I will be talking about the intermixing disorder. So I will show you how it can be elucidated because it's quite a tricky phenomenon in this group of materials. And then I will show by the results of my cooperation partner how does it affect the magnetic properties of these phases. So as it happens, real materials are much more intricate than simple models. And in this class of compounds, there is increasing understanding that the topology is very intimately affected by this intermixing disorder. So let me start by expressing my deepest gratitude to all the wonderful people who are involved in this project. So first of all, the members of my own group who grow the samples despite all the hurdles and then analyze their composition and structure. So this work was mostly done at the University of Dresden, at the Leibniz Institute in Dresden. Therefore, you see the logos here, but recently I've moved to Amsterdam, so I will continue that work. But all I'm showing you today was basically done in Dresden. Many more nice experts from different fields, experimental physics, theoretical chemistry, were involved in this research. So you see the names and some faces here. There will be also a complementary talk later in this afternoon session about the surface spectroscopy of these materials given by Hendrik Bentmann. And last but not the least, I would like to also thank very much the group of Evgeny Chulkov, the theoreticians from San Sebastian in Donostia, who gave the impetus for this study because they made the first theoretical prediction that this manganese bismuth tellurides, bulk periodic compounds, could be intrinsic magnetic topological insulators. So many more people worldwide are nowadays involved into the research of this family. So manganese bismuth telluride 1 to 4 has already been the topic of many articles, exploding from 2019 when the first complementary study on it appeared in Nature. So those of you who attended the tutorial earlier in this conference on Monday given by Mikhail have already learned about these compounds and how important it is to have this out-of-plane ferromagnetic coupling in them, and additional symmetry arising from this fact is taken into account when the topological invariant is calculated. I would also like to point out that these materials are not only predicted to be an interesting platform for quantum anomalous Hall effect, but this effect was actually already observed in thin film of manganese bismuth telluride and published 2020, so leading this theoretical prospects of having intrinsic magnetic topological insulators to fruition. As I said, my group is mostly interested in material science, so materials aspects of these phases, and therefore I will be talking about the, let's say, the base level of this research, how to obtain these materials, how to understand their compositional and structural peculiarities, and how that further perpetuates into their properties and ultimately into their topology. So as we will see, lots of very tiny subtle aspects have to be taken into account. So let me start by a very quick historical survey, so to speak. So extrinsic doping of magnetic TIs is a long-term topic. So already as early as 2010, there were experiments and subsequent theoretical predictions dealing with intercalation of transition metals into the classic topological insulator, the primer bismuth telluride. And manganese back then did not seem like the best choice of a transition metal for doping. So if we look at this experiment here, only at certain concentrations of doping, a ferromagnetic easy access ferromagnet has been observed in this material, and the transition, so the critical temperature was relatively low. Well, it is still quite a bit higher than what was obtained for extrinsically doped heterostructures on bismuth telluride, these chromium-based heterostructures where quantum anomalous Hall effect was observed, but still it was not as striking. So these low expectations for extrinsic manganese doping were further substantiated also by theory that looked at this modeled compound, so manganese taking up some place, so crystallographic positions of bismuth in the structure of bismuth telluride. They calculated that indeed this configuration should show a ferromagnetic ground state, but the resultant magnetic gap at the Dirac point would have been very, very small, so not substantially large to provide robust quantum anomalous Hall effect. Well, some research in that direction has continued, and people started noticing some discrepancies. So let's say the result of this research, a more closer look at the magnetically doped bismuth telluride, has resulted in this very nice paper provided by the Rada group in Berlin, where they looked at the manganese doped bismuth telluride a little bit more closer and noticed that there are not only quantuple layers there that correspond to the well-known structure, tetradimide type structure of bismuth telluride, but there are also septuple layers there unexpectedly. So the septuple layers obviously have a different structure. They were also shown to contain manganese. So they were naturally the first candidate to be looked at and the first candidate to probably be responsible for the topological properties of these heterostructures. Even more interestingly, these heterostructures of quantuple and septuple layers also showed quite larger magnetic gaps than was anticipated by theory for a manganese doped, extrinsically doped bismuth telluride. Further on, people started approaching the septuple layers from a different side. So 2013, there was a first paper reporting that probably a bulk compound with stoichiometric ratios of manganese and bismuth can exist, and that this compound may be built out of the septuple layers, exactly the same ones that were observed in this heterostructure. The problem back then was, as reported by the authors of this paper, that the compound seems not to be very stable. All attempts to quench it from the higher temperatures and to get a crystal or somehow characterize its physical properties have failed because it seemed to decompose as the temperature is decreasing. So with all this prior information and thanks to the very fruitful exchange with a group of Mikhail and Yevgeny Chulkov, we were very interested to start looking into this material system. And we found indeed that this compound exists, but requires very precise and somehow complex synthetic conditions to be obtained as a single crystal. So it took us some time, so several years after the first publication, but then we succeeded and grew this crystal, giving the access to the elucidation of the physical properties. So let me briefly summarize what we have done on the material side, why it was so challenging. So first of all, when you start synthesizing this compound, you have to deal with the starting materials that have very different melting temperatures. So basically you have solid manganese telluride and you have melt of bismuth telluride that melts almost 500 degrees lower. And then when you grow crystal from this melt, it is a heterogeneous solution. Then, so as one can see from this differential scanning calorimetry data, when you start to crystallize the melt, so we are going down in temperature here, you first hit the crystallization peak of the ternary compound. So this 1 to 4 phase that you want to have. But then very soon after, only 10 degrees below, you have crystallization of other solids, one of them being bismuth telluride itself, and another one being another heterostructure in this family that I will talk about a bit later. So that means that if you are a materials researcher who wants to grow a crystal of this phase of a sizable size, you can only cool down the melts in this very small region between the crystallization peaks, which also entails very precise control of the synthetic temperature. And may I tell you, so in modern tube furnaces, there are very often fluctuations up to 10 degrees, despite the very good control of thermocouples. Therefore, you need a whole array of these thermocouples next to your ampule to ensure that you don't cross this borderline. So if you played your cards right and you cool down your melt correctly, you may get nice crystals of these heterostructures, indeed ordered. So you will have a bulk periodic compound with a site for with a defined crystallographic sites for bismuth and manganese. And in this system, you can also get access to further representatives of the family. So natural heterostructures where septuple layers periodically alternate with the quintuple layers of bismuth telluride. It gets progressively difficult to obtain these compounds because the melting points of these further analogs get closer and closer to the melting point of bismuth telluride. Therefore, when you get into the area of 1,610 and 1,813 compositions with 2 or 3 quintuple layers between the septuple ones, you're basically fighting against small fluctuations of temperature kinetics. And despite all the tricks, you may end up with a different compounds that you would like to. That naturally leads to some variety in the reported results on these phases, but there is even more complications that are connected to the structure of these materials. So when we looked at the obtained crystals of 1 to 4 phase by single crystal X-ray diffraction, we noticed that there is always intermixing disorder, antisite disorder in this phase. So this position is not purely manganese and this position is not purely bismuth, but it has some intermixing with the other cation. So you have some bismuth on the manganese place in the central position and some manganese on the bismuth place in the outer position of the septuple layer. Surprisingly, when we tried to synthesize further crystals of this type by varying the conditions, we would always end up with more or less the same intermixing pattern for 1 to 4 with bismuth. So it can be argued that it is somehow kinetics controlled. We are limited, of course, by this very narrow temperature range where we synthesize the crystals, but it could also have some underlying electronic or structural effects that we are not aware of. Despite all the efforts, we could not find any additional superstructure ordering, so this disorder is truly statistical. Furthermore, in all the compounds of this type that we obtained with bismuth telluride layers in between, some degree of disorder was also present. So here you can see some ratios that we obtained for our phases from the X-ray diffractometry. There were also reports by other groups, so from the neutron powder data as well as from STM, that 1 to 4 phase is indeed slightly disordered. Back then, when it came to 1 to 4 compounds, this was not considered as detrimental, so it was close enough to the idealized composition, and the theoretical predictions on the idealized composition would also hold true for what was observed in magnetometry and partially in surface spectroscopy. So this disorder was considered a little bit like as an annoying factor, but not something that actually drives the properties of the material. One can see it also on the consistency of the magnetic properties of 1,2,4 phase that was reported to be a three-dimensional antiferromagnetic compound. So you have here out of plane ferromagnetic coupling between the manganese 2+ sides in each septuple layer, and then they order antiferromagnetically in the interlayer direction. So this data, as I said, was obtained also by many other groups, and the role of these additional interstitials, manganese in the bismuth position, was back then not that obvious. Some problems started when we moved and other groups moved to the characterization of magnetic properties of higher analogues, 147, 1610, 1813 phases. So there it was noticed that the antiferromagnetic transition that sets off at a lower temperature, so naturally you dilute the stacking with the non-magnetic spacers, and the interlayer exchange coupling reduces, so the transition shifts from 24 to about 13K. So this onset of an antiferromagnetic transition is very quickly followed by something that looks like a metamagnetic transition into a ferromagnetic-like, so not the hysteresis here phase. Interestingly, in 1610 compound, there was not even a visible kink corresponding to the antiferromagnetic transition. We almost immediately saw something that looks like a ferromagnet. So in this paper, our collaborators developed a very nice explanation for this fact. So they said that in fact, this metamagnetic transition, so this antiferro versus ferromagnetic ordering is in fact an interplay between the exchange coupling that is being subsequently reduced as we dilute the phase with more bismuth telluride, and the uniaxial anisotropy. But also in the series of our MBT samples, so here we have the whole family from 1,2,4 to 1,813, that seem to be very nicely followed. So you can see that the phases are getting more ferromagnetic-like as one moves towards 1,813. However, when we looked at the data reported by the other groups, we started to notice a lot of inconsistencies in this elucidation. So many other groups, so I only chose two examples here because there was also a characterization of the composition and structure. So many other groups observed that in fact 1610 phase is looking like an antiferromagnet, yeah, more or less. And even in 1813, you can still observe in some other reports a small onset of the antiferromagnetic transition. So what that could be, one of the ideas that now is starting to become more prominent is that these phases may have different distribution of manganese over over two cationic sites. Here, allegedly, two things will play a very important role. So first of all, the overall composition. So you may have some sub-stoichiometric phases, you may have some voids in the cationic sites, or also the ratio between the manganese and the bismuth in each position, because it may promote a different type of coupling between the central position and the outer position. So far, there is no consistent theory that would describe all the possible cases, just because it is also very variable. But those of you who are used to this notation may notice that I here shows the example of 1610 compound, that the results are also quite different with respect to the overall composition and the distribution of manganese between the voids. So we have consistently under sub-stoichiometric samples, while other groups may get a little bit closer to one or even lower in the manganese content. So we are now looking a little bit more carefully into the manganese bismuth telluride family, trying to find out what are the connections between the population of the crystallographic sites and the magnetometry. This is notoriously difficult because, first of all, you have very small values of these additional concentrations, and second, it's difficult to obtain these crystals. Meanwhile, there are new studies emerging. So it was also recently discovered that an antimony analog of MBT can exist. And I will be moving to that phase in a second, showing you that there the disorder phenomenon gets even stronger and it becomes possible to somehow study it not under a looking glass, but let's say at face value, which is already being done. So there are two very nice papers here from the different groups reporting on what can happen in the MST analog. So let me go there and start by presenting the data that we got in our group. So we tried to grow these analogs by slow cooling of the melts. We quickly saw, just like other groups, that this compound does not have a narrow range of stability. It exists in quite a large interval, so it can be obtained in different temperatures. But then when you get your crystal or your powder at a certain temperature, it may have slightly different composition and therefore different magnetic properties. So here I'm talking about crystals obtained at 610 degrees centigrade, and as you can see, this is also sub-stoichiometric, so manganese is below 1, and we have intermixing. Those of you who could mesmerize the percentages in a manganese bismuth telluride would notice that here in the outer position, we have 3 times more manganese. And here we have a ratio between antimony and manganese closer to 1:1, while in the bismuth phase, it was more like 1:3 or 1:4. So we have much stronger intermixing. Well, what are the consequences of that? The consequences of that is a much larger variety of what is observed for the magnetic properties. So as I said, here in bismuth, everybody reached consent. It's an antiferromagnet. Here with MST, there is everything possible. So there are now reports that tell you it is antiferromagnetic. There are reports with ferri or ferromagnetic ordering in this phase with very different critical temperatures. And our own data, dependent on how do we obtain our powders or crystals, also shows that we are dealing with a ferro or ferrimagnet with a very varying temperature of the magnetic transition. So let me show the results we get on the single crystals with the highest TC. So this is at about 44, 45 Kelvin dependent on the sample. So here we have very strong out of plane anisotropy. So it's again an easy access ferromagnet. It is not yet clear whether the coupling between these two sides within the septuple layer is antiferromagnetic or ferromagnetic. The total saturated, so the saturated magnetic moment is still quite low than would be expected for the full manganese 2+ configuration. And interestingly, if we get our samples in a slightly different way, the overall magnetic scheme looks the same, but the temperature keeps on shifting towards lower values. So by now we have certain statistics on the samples. It's very interesting now to compare them between themselves as well as with the reports of other groups. So don't be afraid that I'm showing a very full table of numbers. Just like you, we are also still trying to make sense out of it. But there are already some traits here that can be named and that also are observed in principle by other groups. So let me walk you through it. If we look at samples that are obtained at the same temperature, but are annealed with a different annealed with different duration, we observe increasing disorder. So if we first had more manganese in the central position and less manganese in the outer one, if the sample is a little longer, it starts to become different. Nevertheless, we always observe slight sub-stoichiometry of the samples. Even if we produce them at higher temperatures, there is still quite noticeable sub-stoichiometry of manganese. And all these temperatures tend to cluster at around 27 or 30 K. One could maybe argue that with increasing temperature, we have slightly more manganese, we have slightly less manganese on the outer position, but so it could be a counter-propagating trend. However, it seems to not agree well with what was reported by the Oakridge group, where they observe by their synthetic method different from us that the overall manganese content in both positions is increasing with the synthetic temperature. Interesting in that respect is the observation done in this archive paper by the Rada group and Chulkov group. So there they studied MBE grown thin films and they saw overstoichiometric manganese composition. The calculations there predicted that when we are having only the exchange of manganese and antimony between the positions, so the overall composition stays the same, the ordering temperature should be at about 20 K. It does not really vary too much with the disorder, but as soon as one adds about 5% of manganese excess, so we are going over stoichiometric, there should be a drastic increase in TC. Wow, seems like it is also hold true for our bulk samples. So the ones with the highest TC that we observe also maybe are over stoichiometric in manganese content. So while it will take quite some time to study this matrix, to make some sense out of it, it would be very interesting to see more calculations done on the disordered models that of course very quickly becomes a very large superstructure if you really want to look at the disorders of 5 to 10%. So here I'm not showing any details from my group in cooperation with theoreticians or other groups of theoreticians working on these disordered models. This is still quite ongoing, but I want to show you that in fact this family already with the idealized compositions was found to be very flexible. So if 1 to 4 should be an antiferromagnetic topological insulators already, or insulator, already for 1 for 7, different possibilities become feasible. So the energetic difference between different magnetic ground states becomes smaller, and one could imagine a scenario in which this compound becomes ferromagnetic or antiferromagnetic, giving an antiferromagnetic Ti or a Waals semi-metal. While if the idealized composition is already prone to such flexibility, it's very well possible that the disordered models will provide an even larger playground for coupling different magnetic ground states and the topology, if we will be able to, first of all, discern the value of different factors, and second, to control the samples so well that we can deliberately produce these different stoichiometries. Well, with that, I would like to wrap up my talk and to invite you to listen to the follow-up of it given by Hendrik Bentmann later in this session. He will be touching upon surface spectroscopy experiments performed on our samples. There, it was also observed that this theoretical prediction does not really hold all too well for these phases. So there are some intricate things with a gap being opened in the paramagnetic state, or some other samples different from ours being reported to have a closed gap in the ordered state. There were possible explanations for that in the literature, pertaining that there could be some disorder of the moments at the surface of the samples. I think that nowadays we can also safely say we should look more into disorder, into intermixing in the samples to maybe be and maybe be able to explain these discrepancies in spectroscopy. Here on my last slide, I summarized what is now ongoing in the MBT family. Let's say on the material side, we have very exciting prospects. So if it will be understood how to control the TCs and the magnetic order in these phases by adding different transition metals or by tuning the intermixing disorder, we will be able to push the critical temperature higher. And if we also understand how to keep the topological properties, non-trivial topology of the electronic band structure of these phases simultaneously with rising the TC, we will have even better candidates for quantum anomalous Hall effect. Thank you very much for your kind attention. And with that, I finish my talk and am open for questions. Thank you.
Thank you, Anna, very much for this very nice and clear talk. And I see there is a question from Thanasis. Yes, unmute yourself and ask, please.
Okay, thank you very much. Thank you for this interesting talk. And I wanted to ask, in one of the other phases, for example, the 147 phase, it could be that the quintuples with the septuples do not alternate sequentially, but you may have two quintuples followed by two septuples, so it could be a mixing of the layers, let's say, not
sure.
So does it play any role in the magnetic properties, and can you control that with your growth technique?
Thank you very much for this very on point question. Indeed, control of this layer sequence becomes increasingly difficult. So to your last question, if we can control that and if we know that, I can tell you that we know that on certain length scales. So we always study the samples by X-ray diffraction, showing us the periodicity of the crystal lattice. So let's say for small single crystals on the scale of hundreds of microns, we know that there is very little disorder, or let's say macroscopically this crystal is still a very well ordered lattice. So even if there are some defects, some occasional skipping of the layers and so on, they're very low in number. So of course, when we move to larger samples, like, I don't know, ones that are about 1 millimeter in lateral dimension, this is not a single crystal anymore. This is more like a twin consisting of different crystals. We tried, however, to also study these large pieces by diffraction. So in this case, it would be X-ray powder diffraction. And it also shows us that mostly these larger samples are also, they also belong to the same lattice, meaning that to the large extent, they're still ordered periodically. And as for the variation of the magnetic properties, so yes, it exists to some extent. We try to do it deliberately, so to produce samples that are mixtures of two phases. And it was possible to see slight variation of the TC for one phase, and then already a superposition of two different transitions, indicating that we have two different phases. So at least there is no smooth transition in the critical temperature and the general way how magnetization curve looks between the phases.
Yeah, so if you disturb the order, the perfect order, then do you expect a higher TC or a lower TC?
There are very many ways to disturb the order, and then there is also, in my opinion, some critical mass of disorder. Yeah, so if we, I did not study aperiodic stackings, so that are closer to the maybe these heterostructures that I showed on the introductory slides, where you really have statistics. So we don't have such crystals, we don't study them. But I think that mostly for the, so if we look at the energy scales of these exchange couplings between the layers, so already for 147, when you have one spacer, the interlayer coupling, magnetic exchange coupling, becomes much lower than the in-plane one. And I think that this local disorder, so the one with intermixing, is much more affecting the magnetic couplings and the order than the ones over the layer.
Okay, thank you very much. Thank you.
Thank you.
Are there more questions?
Yeah, I have a question. Thank
Yes,
you very
please.
much for the talk. It was super nice. All the data there. I saw that there is, in principle, there should be in the saturation point, the magnetization, the value of manganese should be around 4 or 5 magneton 4. But then I saw many articles when they obtain like 2, you show something like 3 point something. And I wonder if you know which one is the reason why people cannot get the 4 or 5 value that is predicted for 5.5.
So yes, indeed, this is a general trend for this type of materials. So there is one article where I think, so it was a high field measurement. I want to say it about 10 Tesla, but could be 12 or 14, where the saturation has been reached. So the reason for that, as my colleagues in magnetometry pertain, is in very strong anisotropy of these phases. So basically, when you perform the field measurement, you have slightly non-collinear configurations, and it saturates very slowly. So you only have a part of the magnetic moment saturating at lower fields, and the rest happens only at the higher ones.
Okay. Thank you very much.
And there is a question on the chat, and it says, "Hi Anna, nice talk. You also mentioned the MBE growth. Are there also similar disorder for the MBE grown crystals? Thanks."
Sorry, are there? Could you repeat?
Also is there also similar disorder for the MBE grown crystals?
Thank you very much. So as far as I understand the present state of the literature, there is no considerable notable disorder reported for manganese bismuth telluride films. So I'm aware only of 1 to 4 grown periodically as a thin film with 147. There are problems, and if there is disorder, it's minuscule, it's not really being discussed. But in this archive preprint that I showed, that I flashed by on the last slides, that is about MST film, manganese antimony telluride film. Yes, there is disorder. So it was deliberately looked at. It's about 5 to 10 atomic percent in each position. And this is also over stoichiometric samples, so they have excess of manganese. And that apparently very much changes the properties. So they also report a very high TC of about 45 to 50K.
Okay, thank you. Are there more questions? Okay, I have one myself. Among all the materials that you have run, which one would you consider to be the best candidate for a antiferromagnetic topological material?
I'm very much interested now in this manganese antimony telluride samples because the temperature is so high. However, I think we really need to get very consistent spectroscopy data. These are p-doped samples, so it's very difficult to assess whether there is magnetic gap. And if I can answer your question such, I think the most interesting samples would be manganese antimony bismuth tellurides, so quaternary systems, where one would control both the doping on the bismuth side to get a nicely compensated semiconductor and to get enough disorder on the manganese side to have a high TC. Whether it is achievable, that's another question.
Okay. And one last question. Have been there any attempts to like substitute the magnetic atom? Because okay, you change bismuth with antimony, but what about manganese? You cannot substitute it with another magnetic atom?
There is a very nice theoretical paper, once again, from the Chukov group.
Yeah, but I mean experimentally.
Experimentally, it is being tried. So I would say that we are trying it as well. We are aware of some other groups trying that, but it seems not to be very straightforward. So if you just replace manganese, let's say by iron and so on, it does not proceed that easily. It's possible that it is connected to these very specific synthetic conditions that are required, and one just has to search for them. And hopefully one or the other group will get lucky and obtain. So
okay, so experimentally, you only tried iron.
We tried different transition methods and we are still trying.
Okay. Okay, thank you. Are there more questions? Okay, now let's thank the speaker again and let's swap to the next talk.
Yeah, thank you very much for your attention.
Thank you, Anna.